Okay, so now is the time to formally start the basics we are going to discuss in terms of real quantum mechanics. We have been talking about mostly the mathematical part. And start with, we talk about how really Schrodinger came up with his Schrodinger equation. And we'll derive it, and we'll derive it in the fashion in which Schrodinger derived it. So we know that in the earlier 20th century there was this newfound understanding that was coming in picture, that particles, small particles, they have both particle nature as well as the wave nature. So the way Schrodinger approached this problem was that he started with a wave equation. So let's say there is an electric field which is this is one of the Maxwell's equations describing how electric field is traveling in time. And we know the solution is written as ext equals E naught some amplitude I times kx minus omega t. That's a generic solution for this kind of if you forget this is some electric field or something, but this is some equation, and we know this is a generic solution which we can always prove by substituting it back and obtaining that. If you do that, we actually obtain that the whole thing is going to look like minus k square plus omega square over c square E naught I kx minus omega t. The equation is satisfied, and this is called the dispersion relation. And from here we can say that k equals omega over c. It also means that V lambda equals c. Well, so far so good. We know that this is just right now it's classical electromagnetism. But let's now change things to more of particle nature. Let's try to incorporate particle-like properties into that. So it was the photon. If we start talking about electromagnetic field, let's talk about the photon. And photon, for a photon, we know that E is given as h nu. And nu is the frequency of the photon, which is also written as h bar omega. And we know that for photon, momenta is given as h over lambda, which is same as h bar k. K is the wave number. And with these definitions, which satisfy photon particle-like nature, we just go back and substitute it in the wave equation. And if you do that, our electric field, assuming it's not behaving like a field anymore, but it's like a particle, starts looking like I over h bar px minus et. Is the energy, px minus et. Okay, now and we know that if we this particular equation can also be rewritten as, for a photon like, so we have substituted energy term here, but this can also be rewritten, this main equation can also be rewritten as 1 over h bar square p square minus e square over c square E naught e to the power I over h bar px minus et. This is the equation. Now same as bracket, we're giving this thing here, these brackets will give us that e square equals p square c square. nothing surprising. We know that this is how a photon which has zero rest mass behaves. Energy is given as EC. Well, alright. Let's leave photon behind and start talking about particles. When there's a particle, actually we can sort of make an amendment and write E square, which was given by Einstein anyway, much before quantum mechanics. It's P square C square plus M squared C to the power 4. This is our new E square for a particle. And when we do that, this equation here can be rewritten as minus this new found definition of energy when incorporated in quantum mechanics. We can write this equation as P squared minus E square over C square plus M square C to the power 4 psi. We are writing, instead of writing E naught or E, we are including or writing a new variable which is psi, because we see that the coefficient has changed. By coefficient I mean the operator has changed. Here the operator was P square minus E square over C square. This is the new one. So this is sort of a modification that has been achieved now. I mean, this is sort of intuitive. This is out of intuition that I replace it by this, and I have a new, instead of a wave, electric wave, now we have something called a wave function here, a new sort of function. And this kind of, and very analogous to what we saw here, this kind of behavior is achieved by equation, which is written as, so if this is not my primary equation, but this is my primary equation, that is equal to minus 1 over C square. I have to look in my notes because I don't really remember, cannot calculate right away, but anyway, this is what we get. Over H square times psi I over H bar, this is H bar, Px minus T. And if this is my equation, and if I write my psi xt as psi 0 e to the power IH bar actually divided by H bar Px minus T, then the above equation is satisfied. So with this kind of equation, psi t, this is satisfied, equals 0. Here 0 is there. So this is the operator, this is the wave function, equals 0. This is the solution. And these two, if we take this and substitute it in the main equation, this is what we get. And this equation has been obtained by sort of using intuitive argument from this particular equation. Okay. And if we look inside this bracket here, we see that this bracket actually is nothing, but if we actually substitute this back and this is what we get, we can actually rearrange this, and what we get is something called Klein-Gordon equation. This is Klein-Gordon equation. So Klein-Gordon equation was actually, I think it was found by Schrodinger before Klein-Gordon himself. Maybe I'm wrong. Maybe it's named Klein-Gordon by Schrodinger himself. So that's a good question. I never clarified whether it's Klein-Gordon who wrote this equation or Schrodinger who wrote this equation. Okay, we will clarify that and write that in my comment that who actually wrote this equation first. But anyway, this is psi. This is Klein-Gordon, and this here, this is where actually Schrodinger was sort of upset, not happy, because this equation we can study in quantum field theory. This equation actually will not produce, if used in generally real life cases, real life quantum mechanical system, will not produce understandable results. Schrodinger was actually very dejected, not satisfied with this development. But somehow I think he might have been trying something, or he actually, same as going from special relativity to classical mechanics, he actually rewrote this equation. He reduced this equation by writing, this is a relativistic equation because we are using this kind of formula. So he wrote this to a non-relativistic form. And he did that by simply writing energy as mc square 1 plus E square over m square c4. Actually, should be m square c square, mp square over m square c square. And if we expand this, and higher order terms, and this is nothing but mc square plus the kinetic energy part, which is half mv square. And then with this as my new E, I substitute it back to Klein-Gordon equation. And if I do that, then my psi xt actually looks like mc square t phi, and phi is given as psi naught e power minus I h bar px minus the kinetic energy. And with this, if we substitute back, the Klein-Gordon equation actually reduces to something like this. It's square over 2m. And now if we not restricting ourselves to just one dimension, we can actually generalize it to many dimensions, then a 3 dimension. This is what we obtain. I sort of skipped some steps here, but I think I conveyed the basic idea. Okay, and this is Schrodinger's equation. There's Vx missing, but Vx can be incorporated, I think, at this stage here. And then we also have Vx on the left-hand side here. And this actually, the non-relativistic version of Klein-Gordon equation, which actually is called Schrodinger equation, turned out to be very successful in describing or predicting the quantum mechanical non-relativistic system. So it turned out very useful, and that's why it became so famous. And we'll start by, this was more of a information kind of thing. It's not really, you can see there's no, there are intuitive arguments, but there's no fundamental principle that is used in deriving this equation, but more of a historical flavor. But because of its success, it was used, and later quantum field theory was developed, which actually has more of fundamental foundation. And but we are not really going to talk about quantum field theory. But we'll start using Schrodinger equation in following few classes, and see how it's being applied to some particular cases.